Greetings, everybody. So the topic of today's video is chaos-based image encryption, and specifically, we're going to discuss about histogram analysis. So, first of all, let's remind everybody that we are talking about symmetric image encryption, and this means that we are starting with an information signal, and we are using a chaotic source, for example, a discrete map, in order to encrypt this image, then safely transmitted through a communication channel. And at the receiver end, we are using the exact same chaotic image with the exact same key values in order to reverse the encryption process and obtain the original information signal back. And since we are using the same system and the same key values for encryption and decryption, this is why we term this process symmetric encryption. Of course, as you may have seen in many publications, there is a collection of standard images, both grayscale and color, of course, that many papers use to test the encryption. I can provide a link in the description where you can download a collection of such images. So, for chaos-based encryption, of course, there are two standard processes, which are permutation and substitution. And of course, there are many variations on these. But basically, the first one, permutation, it's basically shuffling of the image pixels. So we take the original image, for example, and the first thing that we do is shuffle the pixels of the image in order to disperse the information throughout the whole image file. And the second process, which is actually the much more secure and important one, is substitution. In substitution, we take a specific pixel and change its value. And of course, we do that with all the pixels in the image. So these are the most standard processes in image encryption, okay? So after we perform encryption, we have a series of statistical tests in order to see how strong the encrypted result is. And one of the most important and standard tests, of course, is histogram analysis. Now, let me remind everybody, for an image, histogram basically depicts the amount of, distribution of grayscale values for the image. It basically tells us how many times in the whole image a specific grayscale shade appears. Okay. So naturally, as you can see on the left image right here, when you have some photograph that depicts specific information, obviously, the distribution of the pixels is not going to be uniform, okay? Since the image depicts some information, you are probably going to get some pixel shades that are more commonly appearing in the image, okay? And this is why the Pepper's image, for example, there are specific shades of gray that are more common than the others. And what happens if we shuffle the image's pixels, okay? You will see right here that the shuffled image, so it's the first part of the encryption process, the shuffled image has the exact same histogram. Why? Okay, this is a big question. Why this may happen? Well, if you think about it, it makes absolute sense because let's say I'm taking a deck of cards, I'm buying a new deck of cards, and as I buy it, I take it out and I shuffle the cards. So how many tens do we have? Four. How many jacks do we have? How many queens do we have? Four, always. So regardless of the fact that we are shuffling the deck of cards, the amount of tens, aces, jacks, queens, etc. doesn't change, okay? And this is why the original image and the shuffled image have the exact same histogram because we shuffled the pixels, but the distribution of the pixel values remains exactly the same, okay? And this is a very clear indication as to why performing only shuffling on the image pixels is not a secure process. You need to accompany it with substitution, okay? And as you can see in the fully encrypted image, where we have substituted the image pixels, specifically we have performed exclusive OR here, the histogram is completely uniform, okay? And you can also check the variance below, that it's much smaller than the rest. Basically, the uniform histogram reveals no information about the actual pixel distribution in the image, okay? It is absolutely uniform. This is the desired result from chaos-based encryption, okay? You should always obtain an encrypted image that has a uniform histogram, okay? Meaning that it has no information about the pixel values of the original image, okay? This is the desired result. And of course, this has to do not only with with gray images, I'm sorry, but also with colored images. The process is exactly the same. The only thing different is that we can actually need to study each of the three specific channels separately. So red, green, and blue channels, all of them in the encrypted image should have a uniform histogram. Okay? And I plot the result right here. The original channels, of course, are non-uniform, as you can see. But after encryption, uh, all red, green, and blue channels provide the uniform histogram for the image. So regardless of whether you are considering grayscale or colored images, I'm sorry, the result after the encryption for the histogram should be the same, a completely uniform histogram. So this is one of the first and most important and basic tests performed for chaos-based image encryption. So thank you very much. And in the next videos, we're going to discuss about a series of statistical tests that are very common in chaos-based encryption papers.